In this lecture, we are going to look at the 8086 instruction encoding. Instruction encoding is all about the binary representation of microprocessor instructions. The Intel 8086 instructions are encoded into binary numbers that are 1 to 6 bytes long. This means that the shortest instruction is 1 byte long and the longest instruction is 6 bytes long. The first byte is the opcode byte. This is the byte that tells the operation to be carried out by the instruction. The second byte is the addressing mode byte. This byte tells the location of the operands as well as the destination of the results of the operation. The next 4 bytes are used for direct address values, displacement values, and immediate data values. The direct address value or displacement value immediately follows after the addressing mode byte. The immediate data values follow after the address value or the displacement value. It is important to note that direct addresses, displacement values, and immediate data values can be 1 or 2 bytes long. Hence, these respective fields can be 1 or 2 bytes long depending on the length of the address, displacement value, or immediate data value that is required by the instruction. When there's no address value in the instruction, the immediate data value immediately follows after the addressing mode byte. This illustration shows further information about the bytes that make up an 8086 instruction. It shows the fields that make up the opcode and addressing mode bytes. It also shows the arrangement of displacement values, direct address values, and immediate data values. 16-bit direct address values, displacement values, and immediate data values are encoded starting with the lower byte. As can be observed from the illustration, the lower byte of the address or the displacement comes after the addressing mode byte. After that, the higher byte of the address or the displacement value follows. After that, we have the lower byte of immediate data followed by the higher byte of the immediate data value. Let's zoom in on the fields that make up the opcode and the addressing mode bytes. These fields are the opcode field, the destination field marked as D, the width field marked as W, the addressing mode field marked as mod, the register specifier field marked as reg, and the register or memory specifier field marked as RM. The opcode is a 6-bit field that tells the operation to be carried out. W is a single-bit field that tells the width of the operands. If W is 0, the operation is carried out on 8-bit operands. If W is 1, the operation is carried out on 16-bit operands. Reg and RM are fields that are used to specify the locations of the operands. Since there are 2 fields that specify locations of operands in 8086 instructions, it means 8086 instructions can specify up to 2 different operands. Reg is 3 bits wide and is used to specify a register as the location of one of the operands. Up to 8 different GPRs can be specified by the range field. RM is 3 bits wide and is used to specify either a register or a memory location as the location of the other operand. Mode is a 2-bit field that is used to specify the addressing mode to be used with the RM field. Combined, the RM field and the mode field give up to 32 different ways of specifying the location of the second operand. 8 of these ways refer to the GPRs. The other 24 are the different ways in which the address of an item in memory can be specified. D is a single bit field that is used to specify the destination of the results. If D is 0, the destination is specified by the range field. If D is 1, the destination is specified by the RM field. There are some instructions that explicitly specify only one of the operands. In such cases, the RM field is used to specify the operand. The range field is then used as an extension of the opcode field. We shall go into the encodings for registers. Registers are encoded in the range field as well as in the RM field when mode equals 11. Registers can either be 16-bit registers or 8-bit registers. Whether an instruction refers to 16-bit registers or 8-bit registers is determined by the state of the W field. For 16-bit registers, AX is encoded as 000, CX 001, DX 010, and so on as shown on the illustration. For 8-bit registers, AL is encoded as 000, CL 001, DL 010, BL 011, and so on as shown on the illustration. When the mode field equals 00, 01, or 10, the RM field specifies a location in memory. In other words, the operand is located in memory and the RM field specifies the way in which the memory address of the operand is determined. For the case mode field equals 00, the patterns 000 through to 011 in the RM field specify base index addressing of the operand. The base and index registers are as shown in the table. The pattern 110 specifies direct addressing of the operand. The 16-bit address of the operand follows the addressing mode byte in this case. The patterns 100, 101, and 111 specify indirect addressing of the operand. The pointer registers are specified as given in the table. For the case mode field equals 01, the pattern 000 through to 011 in the RM field specifies based index with displacement addressing for the operand. The pattern 100 and the pattern 101 specifies indexed addressing with displacement for the operand. The pattern 110 and the pattern 111 specifies based addressing with the displacement for the operand. The base registers and the index registers for each pattern are as shown in the table. All the displacement values in this case of the mode field pattern are 8-bit values, and these values follow the addressing mode byte. For the case mode field equals 10, the patterns 000 through to 011 in the RM field, specify base index addressing with displacement for the operand. The patterns 100 and 101 specify index addressing with the displacement for the operand. The patterns 110 and 111 specify based addressing with displacement for the operand. The base and index registers are as shown in the table for each of the patterns. All the displacement values for the case when mode field equals 10 are 16-bit values. The displacement follows the addressing mode byte in the instruction encoding. We have an example here to illustrate instruction encoding. We are going to use the instruction move dx. The instruction moves the contents of register bx into register dx. The binary representation of the instruction is as shown on the illustration. The opcode is the uppermost 6 bits of the binary pattern, here shown in red font. There are 2 operands, and these are located in registers dx and bx. We put the register dx in the reg field, so it is shown here represented by the pattern 010 in the reg field. We put the register bx in the RM field. It is shown here by the pattern 011 in the RM field. To make the RM field refer to a register, we put the pattern 11 in the addressing mode field. The operands are 16-bit wide because they are located in registers that are 16-bit wide. Therefore, we put a 1 in the width field of the instruction. The destination of the operation is register dx. Register dx is specified by the reg field. Therefore, since our destination is specified by the reg field, we put a 1 in the destination field. The second example uses the instruction sub in brackets DI-BP. The instruction subtracts the contents of register BP from the contents of the memory location pointed to by DI and stores the results in the memory location pointed to by DI. The operands, therefore, are the register BP and the memory location specified using indirect addressing with the pointer register being DI. The binary representation of the instruction is as shown on the illustration. Thus, the opcode, and it is the 6 uppermost bits of the binary representation. The register BP is specified in the reg field, and the corresponding pattern is 100. The pointer register DI is specified in the RM field, and the corresponding pattern is 111. Since the RM field here is used to specify a memory location, we put 00 in the mode field. The pattern that we chose here matches the indirect addressing that we are using to specify the memory location. The width of the data is 16 bits because one of the operands is contained in a 16-bit register, that is contained in register BP. Therefore, we put a 1 in the width field. The destination is specified by the pointer register DI. The pointer register is specified in the RM field. Therefore, we put a 0 in the destination field of the instruction. In the Intel 8086, 16-bit address values, displacement values, and immediate data values are stored in memory using what is known as the little endian style. In this style, the lower byte is stored at the lower address and the higher byte is stored at the higher address. In other words, the value is stored starting with the lower byte or is stored in a reverse order. For example, if the value 5687H is to be stored in memory starting at address 7000H, then it will be stored as follows. 87H is stored in memory address 7000H, 56H is stored in a memory address 7001H. We can notice that the value has been stored in a reverse order. It is important to note that only the bytes that make up the value are stored in a reverse order. The individual bits within the respective bytes retain their order. It is also important to note that when we quote the address of a 16-bit value, we quote the address of the lower byte. If 16-bit address values or 16-bit displacement values are part of an instruction, the opcode is stored first, followed by the addressing mode byte, then the address or displacement value in a little endian style, and the immediate data value in a little endian style. Let's have an illustration using an instruction that contains a direct address. The instruction that we're going to use as an example moves the contents of register BP into a memory location whose direct address is 4508H. So therefore, the operands are register BP and the direct address 4508H. The binary representation of the instruction is as shown on the illustration. The opcode byte and the addressing mode byte are obtained using the approaches that we have already described, and it comes out as shown on the illustration. Different fonts have been used to represent different fields within these two bytes. The direct address is a 16-bit value. This value is encoded in a little endian style and is stored following the addressing mode byte as shown on the illustration. We now have an illustration for an instruction that contains an immediate data value. The example instruction that we are going to use is the instruction that adds the immediate value 5600H to the value in register CX and stores the result in register CX. The binary representation of the instruction is as shown on the illustration. The opcode and addressing mode bytes are generated as per the descriptions made earlier, and they come out as shown on the illustration. The immediate data value is encoded in a little endian style and comes after the addressing mode byte as shown on the illustration. The 8086 instruction set given in Appendix A of the notes is organized into three tables. The first table in Appendix A gives the meanings of the opcode mnemonics. The second table in Appendix A2 gives the assembly syntax for the 8086 instructions. The second table in Appendix A3 gives the binary construction of the 8086 instructions. Shown here is an extract of the table in Appendix A3. It shows the binary constructions of a couple of 8086 instructions. Opcode bits are always given for each instruction. The direction bit, the width bit, addressing mode bits, register specifier bits, and RM specifier bits may need you to make a choice depending on the type of and location of the operands in the instruction. You will use the approaches described earlier to build these fields. In addition, displacement and immediate data values will need you to work out from the assembly instructions. For the complete list of non-numerical symbols and their meanings, there are notes that are given at the end of the table. These notes describe what the symbols are used for, as well as how to get corresponding binary patterns for different cases. You may further study this table and then use it to generate binary representations of various assembly instructions. The illustration shows the different possible instruction formats found in the 8086 instruction set. All the instructions have at least an opcode byte. In 1-byte instructions, either the operand is implied or there is a 3-bit field in the opcode byte to specify the register to be operated on. The rest of the instructions have at least an opcode byte and an addressing mode byte. 2-byte instructions have only the opcode byte and the addressing mode byte. 3-byte instructions have the opcode byte, the addressing mode byte, followed by an 8-bit displacement value or an 8-bit operand value. 4-byte instructions have the opcode byte, the addressing mode byte, followed by a 16-bit displacement value or a 16-bit operand value. 6-byte instructions have the opcode byte, the addressing mode byte, followed by a 16-bit displacement value and then a 16-bit operand value. Instruction prefixes are codes that are added before the instruction to make the instruction execute in a certain manner. For example, the repeat prefix makes the instruction to be executed a number of times. A second example is the segment override prefix. This prefix makes the instruction to use a different segment from the default segment. For example, you may want to access data from the code segment. However, instructions are designed to access data from the data segment. To enable data to be accessed from the code segment, a segment override prefix will be used to make the instruction access data from the code segment instead of the data segment. In assembly format, prefixes are represented using symbols, and these symbols are placed before the opcode mnemonic. There should be at least one space between the prefix symbol and the opcode mnemonic. We have an example shown on the slide. In machine code, the prefixes are encoded into some specific values. The prefix codes are placed before the opcode byte. In 8086, the prefix codes are F0H for the log prefix, F2H for the repeat if not equal or repeat if not zero prefix, F3H for the repeat if equal or repeat if zero prefix, 2EH for the code segment override prefix, 36H stack segment override prefix, 3EH data segment override prefix, 26H extra segment override prefix. The prefixes are organized into two groups. An instruction can only use one prefix from a group at any given time. We go into an exercise. Do all the questions from chapter 4 tutorial questions exercise set D and submit responses for the questions indicated on the slide via the Google Classroom platform.